Okay, so the next speaker is Cameron, talk about tolerant independent set testing.
Okay, yeah, hi everyone, my name is Cameron. This is called the Tolerant Independent Set Tester. And I'll just mention I'm at the University of Waterloo. I'm starting my last year of my PhD, and I'll be applying for postdocs later this year. So if you're looking for a postdoc and you like this work, I'd love to chat afterwards. Okay, so let's start with the independent set problem. So given a graph on n vertices, does it have an independent set of size rho n? Where an independent set is just a set of vertices such that no two vertices are adjacent. So this is one of the classic NP-complete problems. So it's believed to be hard to solve. It's even believed to be hard to approximate solutions to this problem. And many other variations of this problem seem to be hard to solve. But it turns out there's a testing version of this problem that's actually quite easy. So what is this testing version? So now we want to distinguish between the case that our graph has this independent set of size rho n and the epsilon far case. In other words, every induced subgraph of size rho n has at least epsilon n squared edges. So in other words, you'd have to remove at least epsilon n squared edges to make the graph satisfy that property. So it turns out this easier version of the problem, this was one of the problems studied by Goldreich, Goldwasser, and Rahn when they first studied property testing in the 90s. And what they showed was that you can distinguish between these two cases with high probability by just taking a random set of rho over epsilon to the 4 vertices, querying all the possible edges between these vertices, and just by looking at that small number of edges, you can distinguish between these two cases. So this is kind of surprising because the original independent set problem was hard to solve, and now if rho and epsilon are constants, this is just like a constant number of vertices and edges that we're going to look at. Where I'll mention that this tilde here is just hiding log factors in epsilon and rho, but not in n. And I'll mention we're going to call this the sample complexity. So we're looking at, these are called canonical testers that take a random set of vertices, and we're just going to count the number of vertices that are in the sample. So we're going to call it sample complexity. Okay, so here's the theorem again by GGR. And in some prior work with Eric Blay, we showed that we can improve this to rho cubed over epsilon squared. So we improved both the rho and epsilon dependence. And it turns out this is optimal up to logarithmic factors by a lower bound by Feige, Langberg, and Schechman. So at this point, the standard testing problem seems to be quite well understood. But ideally, we want something a little more robust. And so maybe to understand that, let's consider this example. Suppose we had a graph, maybe take like a complete graph, and then take rho n vertices and remove all the edges except one. And, well, what does the standard tester say about this type of graph? The problem is this graph really does not fit into either of the two cases. And so our standard testing algorithms really have no guarantee. But in many cases, we maybe would want to accept this type of input. Maybe we can think of this being like a yes instance, like it had the rho n independent set, and there was a bit of noise or something. So maybe we'd like to accept this type of input. And this motivates the idea of tolerant testing, which was introduced by Parnas, Rahn, and Rubenfeld for really any testing problem, but of course we're just going to look at the independent set problem. So now we have an epsilon 1 and an epsilon 2 parameter, and we now want to distinguish between the case that the graph is epsilon 1 close, which means that we have some rho n vertices that form like a sparse subgraph, from the epsilon 2 far case, which is the same as before. And any algorithm that can distinguish between these two cases, we'll call an epsilon 1, epsilon 2 tester. So a few things to note here. This is nice because it generalizes the standard testing problem. So if we plug in epsilon 1 is 0, then we just get the standard testing problem. But in general, epsilon 1 may be a function of epsilon 2, and one parameter range of interest is when epsilon 1 is roughly on the order of epsilon 2. And it turns out in some other models, there can actually be an exponential gap in the query complexity of the standard tester versus the tolerant tester in this parameter range. So what about the independent set property? And what we show is that really there's actually no gap at all. So in this parameter range where epsilon 1 is roughly on the order of epsilon 2, there's a tolerant tester for the independent set property with sample complexity rho cubed over epsilon squared. And so up to logarithmic factors, this matches the same sample complexity bound for the standard tester. And in fact, the approach that we use here is going to be a generalization of the approach in the prior work, which was this, they used this graph container method. So I'll mention a little bit of that in the next 5 minutes. I'll also mention, so this problem wasn't studied directly. However, you could get a tolerant tester from some prior results about testing general graph partition properties. And so doing that, you could get something on the order of 1 over epsilon to the 12, and so we would improve on that. Do you have a question?
Yes. So previously you mentioned like one of the interesting regimes is when epsilon 1 is ordered epsilon 2.
Yeah.
So does your result also extend there potentially with a large sample complexity, or it doesn't apply?
Yeah, good question. So ours is not, so was your question like a fully tolerant tester? Is that
Yes.
Yes, so ours is not a fully tolerant tester. And that's kind of one of the open questions of can we use this container method to kind of get a fully tolerant tester. So this result here, the nice thing about this is it was a fully tolerant tester. But it's just, they haven't optimized, well, it's applying for a much larger class of properties, so they weren't trying to get this optimal.
So do you think this is possible to make your tester fully tolerant, or that there might be a gap? What is your concept?
We're currently working on this. I think we can. I don't know if with the container method we're going to be able to get this same bound. But I feel like, I mean, we know there is a fully tolerant tester with this bound. Surely 1 over epsilon to the 12 is not the right bound. Whether it's this, I'm not so sure. Yeah. Okay, so I'll just mention a little bit about what our algorithm is and maybe just mention what the container method is. Okay, so what is our algorithm? Again, we're trying to distinguish between these two cases. Either we have a sparse subgraph or every row n set is sufficiently dense. So what's the testing algorithm? One nice thing is the testing algorithm is actually going to be maybe the first thing that comes to mind. So what you're going to do is take a random set of S vertices and inspect the induced subgraph and check to see if there is a row S subgraph within your sample that has a small number of edges. So it's not too hard to show that in the yes case, you do have this sparse subgraph, and your sample should find a reasonable number of vertices from that sparse subgraph. And with reasonable probability, these themselves should be sparse. So we should accept, which is what we want. And the hard case is showing that when we are epsilon far, we will not find such a sparse subgraph in our sample. And this is where we would use this thing, the container method, which was also used in the prior work. So maybe just the 1-minute intro on what is the container method, if you haven't seen it before. What is the container? All right. So usually the container method is a tool for characterizing independent sets in graphs. So I like to use this example to illustrate it. So this example has lots of independent sets. If I've counted correctly, there's like 25 of them, and I've circled just 3 of them. What the container method says is that there could be a lot of independent sets, but there's a collection of containers where each container is a subset of the vertices that can cover all of the independent sets. So in this example here, again, lots of independent sets, but I can give you these 3 containers, which are subsets of vertices, such that any independent set is fully a subset of one of these containers. So this is kind of surprising. I've only given you 3 subsets here, and I'm claiming that they've covered all of them. But that's kind of the goal. And usually what we're aiming for is 2 things. Number 1, the containers are not too large, because I could just give you the entire subset of vertices, and that's not interesting. And also there's not too many of them. Because again, I can give you all 2 to the n subsets. Okay, so I'll skip over this. Basically, you can formalize this in many different ways. There's tons of applications in combinatorics. the prior testing results, strengthen this and use that in their analysis. The punchline is that in this work, what we had to do was prove something that looks like this, but for sparse subgraphs instead of independent sets. And that was really our main contribution, is making this work for independent sets, which really had not, the parameter range we were interested in had not been done before in any of the combinatorics literature on container methods. Okay, so just to summarize, we gave this new container limit for sparse subgraphs. This gave us a tolerant tester with the same sample complexity as the standard testing bound. Some of these only questions, one of this is a fully tolerant tester, but maybe I'll just leave it at that. So thank you.
Any more questions?
Let's talk about the straightforward algorithm. Just take the correct. What we believe is the correct amount of vertices and just look for the subgraph. Why would it fail when epsilon 1 and 2 are not exactly as you did with the this specific epsilon 1?
Right. Yeah, I guess what is difficult to argue about the structure of these graphs. So if you're epsilon too far, what we're trying to argue about is like, what do these sparse subgraphs, what's the structure of them in the graph? And why the tester would fail is like, it just might find one of these, that's the short answer, but like, where does the analysis break down is when we're trying to find these like containers for these sparse subgraphs, if they're too dense, then the container method just doesn't work. The container method is really designed for independent sets. And as they get denser and denser, the method starts to break down.
Okay, so if the problem is dense, like subgraphs, so if I use epsilon 1 smaller than this one, it should
Exactly,
work.
yes. Any epsilon 1 smaller than that value works. Yeah.
Oh, okay. Thank you.
Sorry, I don't know much about this area, but are there any connections between this container method and this like semi-ready regular lemma that I know is also used in property testing?
This is a good question. This is something that we're exploring right now. Immediately, it doesn't seem to be like the regularity lemma is saying a much stronger statement, but I think this is a very good question, so I'm trying to explore this. Yeah, thanks.
Okay, let's stay in this.